In this video, we're going to start to look at the motion of objects. And first, we're going to identify that if an object is moving in a particular direction and all the particles are moving in that direction, then we're going to treat the object as a point-like particle. And we're going to identify that the position of a particle is its location on some scaled axis or some coordinate system, and we're going to apply the relationship between a particle's displacement and its initial and final positions. We're also going to apply the relationship between the particle's average velocity, its displacement, and the time interval, and apply the relationship between a particle's average speed, a total distance it moves, and the time interval. And finally, given a graph of the particle's position versus time, we'll determine the average velocity between two times. This unit, we're going to discuss the topic of kinematics, and kinematics is the classification and comparison of motion. Now, this first section, and actually the first chapter that we're going to cover on kinematics, we're only going to consider motions along linear paths. So we'll get into two-dimensional motion later. This is just one-dimensional motion to start with, and we're only going to discuss the motion itself, not the forces that cause the motion. And we consider the object moving to be a particle. So even though the object may be a collection of particles, we're just going to look at it as one single point mass. When we talk about the position of an object, we're saying that it's the distance measured relative to a reference point. And so we have to have some reference point, and typically that's the origin of our coordinate system, or in one-dimensional motion, it's just the origin of our axis. And so position can have sign. It can have a positive sign or a negative sign. The positive direction is in the direction of increasing numbers. Now, in our traditional Cartesian coordinate system, that's typically to the right, but it's not always the case. It's the positive direction must be in the direction of increasing numbers. Sometimes with convenience we say it's to the right, sometimes we say it's to the left. And the negative direction is the opposite direction. It's in the direction of the decreasing numbers. If an object changes position, we say that change is called the displacement. And we represent displacement with a delta x. Delta meaning change, and then x is just our position. There are other times that maybe we'll use an s or a y if we're talking the vertical direction, but for right now we're just going to use delta x. And what delta x is it takes our final position minus our initial position, or any two positions that we may have. We take the second minus the first. So if we have a particle that moves from the 5 meter mark to the 12 meter mark, the displacement is 7 meters. It's a positive 7 meters because it increased 7 from 5 to 12. If it starts at the 5 meter mark and then ends up at the 1 meter mark, then the displacement is negative 4 because it's going backwards. It's going in the direction of decreasing numbers, and so the displacement is negative 4. And finally, if we have a particle that starts at the 5 meter mark, then travels to the 200 meter mark, and then makes another trip back to the 5 meter mark, then the total displacement is in fact 0 because it started at 5 and ended at 5, so 5 minus 5 is 0. The actual distance covered, and this is important, the actual distance covered is irrelevant. Displacement is not distance. Now, you might argue that these first two examples, displacement and distance, were equivalent, and yes, that is true. That is sometimes the case. But distance and displacement are not synonymous. They talk about two different concepts. Displacement is a change in position. Distance is a length that is covered. Therefore, we say that displacement is a vector quantity. It has both magnitude and direction. And the magnitude is the length or the distance in the case of meters or feet. Typically, we're going to use meters, the SI units. And the direction is along a single axis. So if we're talking one-dimensional motion like we are now, then we can simply just say positive or negative. When we get into two- and three-dimensional motion, we'll have to be a little more specific with our direction. But for right now, it's just positive or negative. If we ignore the sign, then we just have the magnitude. So we could say in that second example, when our displacement was negative 4, the magnitude of our displacement was 4 meters. We are 4 meters away from our original mark. That doesn't tell us the direction. We don't know if we're 4 meters above 5 or 4 meters below, but we know the magnitude is 4 meters. Let's take a look at this quick checkpoint right here. And we have three pairs of initial and final positions, respectively, along an x-axis. Which of the pairs has a negative displacement? So if we start at -3 and then end at +5, we're going in the direction of positive or increasing numbers, so we have a positive displacement of 8. Whereas if we start at -3 and then go to -7, well, that gives us a displacement of -4. And if we start at 7 and go to -3, that gives us a displacement of -10. In both of these, we're moving in the negative direction. We're moving in the direction of decreasing numbers. So both B and C give us a negative displacement. With displacement comes velocity. And we say the average velocity, now keep in mind this is the average velocity, is the ratio of the displacement to the time interval in which the displacement occurred. So we say V average, which V represents velocity, and we can either have a subscript AVG or you can have a V with a bar over it. Both of those mean the average velocity. And so our formula for average velocity is the change in the position over the change in time. The units are distance over time, so that means we use meters per second in our standard units. On a graph of position versus time, the average velocity is the slope of the secant line. So we connect 2 points, our position points, and we find the rise over the run, or delta x over delta t. And so the slope of the secant line is going to give us the average velocity. Positive slope means positive average velocity. Negative slope means negative average velocity. Positive slope means we are changing in a positive position over our time interval, where negative slope, we're decreasing our position. Similarly to average velocity, we have average speed. Now, one thing to keep in mind here, velocity is a vector, speed is a scalar. And so the average speed is the ratio of the distance over the time interval. And so we need to know the scalar quantity of distance and the time interval to get the scalar quantity of speed. One thing to remember is that speed is always positive. Think of the speedometer in your car. It doesn't matter which way you're driving, north, south, east, or west. Your speedometer starts at 0 and only goes in the positive direction. So a quick example here is if a particle moves from x equals 3 to x equals -3, and all of this happens in 2 seconds. And so the average velocity, we would have to look at the change in position over the time. Well, what's the change in position? We go from 3 to -3. The change in position is a -6. And so that happens in 2 seconds. That gives us an average velocity of -3, meaning we're moving in the negative direction, whereas our average speed is just 3 meters per second, because our distance traveled is 6, a positive number, divided by 2. In this case, the speed is just the magnitude of the velocity. That does happen often, but it is not always the case, especially when we have a situation where we turn around. And we'll get into those situations later. Now that we have the basic concepts down, we're going to move on to looking at velocity a little more closely. And so in the next part of the video here, when we're given a particle's position as a function of time, we're going to calculate the instantaneous velocity, and this is where calculus comes into play. And also, given a graph of a particle's position versus time, we're going to determine the instantaneous velocity for that particular time. Once again, more calculus, and then we're going to identify the speed as the magnitude of the instantaneous velocity. And just like I said on the last slide, the speed is not always the magnitude of the velocity. That's when dealing with average. But you'll find here that when we deal with instantaneous velocity, the speed is the magnitude of the instantaneous velocity. So we have to create a separation between what is average velocity and speed and what is instantaneous velocity and speed. So what is instantaneous velocity? And typically we will just say velocity, and when we just say velocity, it's implied that it's the instantaneous. And what this means is it's the velocity at a single moment. So it's a snapshot at that exact instant in time what is the velocity of the object. So what is the magnitude and the direction. And so knowing what you know from calculus, in that when you take the secant slope of a line and you take the limit as the delta t, or the change in the independent variable, approaches 0, that gives us the slope of the tangent line, which is the derivative of the position versus time curve. And remember, what does the derivative represent? Well, the derivative represents the slope of the tangent line. And so all of these ideas are synonymous. And so we can go back to the average velocity, take the limit as delta t approaches 0, then we're going from a finite delta t to an infinitesimally small delta t, and that's where we get the derivative of the position versus time. In one-dimensional motion, the sign of the velocity will represent its direction. When we're talking about instantaneous velocity, the speed is the magnitude of the velocity. And so a velocity of 5 meters per second and negative 5 meters per second both have an associated speed of 5 meters per second. So the 5 meters per second velocity just means we're moving in the positive direction. The negative 5 means we're moving in the negative direction. But in both cases, we have a speed or a magnitude of 5 meters per second. Let's take a look at this checkpoint here real quick. And in this situation, we're given a position function for a particular particle. It doesn't matter what it is. And x is measured in meters, t is measured in seconds, and t is greater than 0. We pretty much always assume t is greater than 0 because negative time doesn't exist. Time is a scalar, and the arrow of time always marches forward. So in these 4 situations, we have different position functions, and we want to know in which situation is the velocity of the particle constant. Well, that means when is dx dt equal to some constant, or just some number. And so let's look at these. Let's look at number 1. The derivative of 3t minus 2 is, well, dx dt here is going to just equal 3, and 3 is a constant, so situation 1 gives us a constant velocity. Let's look at situation 2. Well, if we take the derivative of that, dx dt is equal to a negative 8t. That is not a constant, that's actually in a decreasing function, and so that doesn't fit our situation that we're trying to find here. And same thing with number 3, we take the derivative of that. Well, the derivative of 2 over t squared with respect to t is going to equal a negative 4 over t cubed, which once again is not constant. And finally, let's look at the last position function where x is negative 2. The derivative of that is simply 0. What does that mean? Well, the velocity is 0, and so the position is not changing. And if you look at x equals negative 2, that's just a horizontal line. Now remember, this is x versus t, not y versus x, because you might think in traditional algebra where you have the x and y axis, that's a vertical line, but x is the independent variable in this case. And so this is a horizontal line. The position does not change, and that means there's no velocity. So 1 and 4 both give us a constant velocity. Even though 4 is 0, that's still constant. It's not changing. Whereas situation 2 and 3, those are in the negative direction because we have a negative 8t and a negative 4t cubed. Now, how do we know those are always negative? Well, t is always positive. So if we put in a positive number for t in both of those situations, the velocity is going to be negative. Let's take a look at this last example with velocity, and we have a graph. This is a position versus time graph of an elevator car. And so just looking at the position, we see that it starts at 0 and stays at 0 for a little bit, and then it starts to change its position up to a level of a little above 25, and then levels off there. And so the slope of that function is the velocity, and the velocity is 0 from 0 to 1 seconds because the slope here is a horizontal line. The tangent line is horizontal, slope is 0. and from 9 seconds on. So here we stop and we stay stopped. So what that means is we are stopped from 0 to 1, and then at 1 we start to move. And then at 9 seconds we stop again, and we don't have any other information after those 9 seconds. So the elevator could start again, but we don't have any information on our graph. In between, we are moving, we're changing position. And so the slope of this function tells us how we're changing our position. It tells us the velocity. And so we can graph this. And if we look from B to C, just in that region, from here to here, that is a linear function. The position function is a linear function, so that translates to a constant function in the velocity graph. And so we can draw that as a horizontal line in the velocity graph because the rate at which we're changing does not change. Whereas in this portion from 1 to 3 seconds, that is a curve in the position versus time. So that means that our position is changing, but the rate at which our position is changing is changing. We're going to talk about what that represents in a moment. And so that shows that we have a change in our velocity and we're speeding up, which should make sense. The elevator car is stationary. It speeds up to a max speed, and then it will eventually slow down up here between C and D, and then that translates to a negative slope on our velocity graph. Finally, in this video, we're going to look at the particle's average acceleration and how it relates to the change in velocity. And then we're going to look at its particle's velocity versus time graph, just like the one we just drew. And we're going to see how does the instantaneous acceleration relate to that. And given the graph of a particle's velocity versus time, determine the instantaneous acceleration. So acceleration is very similar to velocity in that it is a rate of change, but acceleration is the change in the particle's velocity. So the change in the particle's velocity over the change in time gives us the average acceleration. And remember, we can have the subscript AVG or an A with a bar over it. Where the instantaneous velocity, using the same logic, we say is the derivative of the velocity function. So if we have a position function, we take one derivative to get the velocity function, take a second derivative to get the acceleration function. Another way we could say this is that the acceleration is the second derivative of the position. It is the second time derivative, and we will often refer to that as the formula for the acceleration function. Just like velocity, acceleration is a vector quantity. Positive means in the positive direction, negative means the opposite of that. And the units are distance per time squared. So typically that's meters per second squared in the standard units. This last note here is very important. If the sign of the velocity and the acceleration of a particle are the same, then the speed is increasing. So a particle is speeding up when the signs are the same. Whereas if the signs are opposite, the speed is decreasing. Another example here is if a car with a velocity of negative 25 meters per second is braked to a stop in 5 seconds, then the acceleration is a positive 5 meters per second squared. And we get that because our change in velocity is a positive 25. We go from negative 25 to 0, and that happens in 5 seconds. And this supports our last statement in that the acceleration is positive, but the velocity is negative, so the speed is decreasing and has decreased. One of the accelerations that we need to have in the back of our mind is that the acceleration due to gravity on Earth is about 9.8 meters per second squared. And so we use a little g to represent this number, and a lot of times we will relate our accelerations to some multiple of g. Checkpoint 3 here is a good exercise to do to practice your sign of velocity and acceleration when speeding up or slowing down. I'm not going to talk about it right now. I'm going to let you do that. So the answers are right here, but go ahead and read through that. Double check to make sure that you have the correct understanding of like sign, speeding up, opposite sign, slowing down. Finally here, we're going to revisit that velocity versus time graph of the elevator car. And so we don't have the position graph here, but remember, from the position graph, we arrived at this velocity graph. And if we want to draw an acceleration graph, then we need the slope of this graph. So we need the dv dt, or the second derivative of the position. And so we do the same thing. We look at, well, whenever this is a horizontal line here on the velocity graph, that corresponds to a 0 acceleration. Whereas whenever we have a linear function, and so this is a linear increase, a linear decrease, that means that's a positive horizontal line on the acceleration function and a negative horizontal line on the acceleration function.